Opening and closing and opening the Texas margin. We start with the Cambrian with distributed rifting, blocks and ribbons, and we'll show a map of that in just a second. We go into the Ordovician. There's probably a mid-Ordovician kind of event that's all off-board, essentially, offshore, and mostly not so much preserved, but it has some stratigraphic effects that are preserved on the Texas margin. Then, after a while of Laurentia floating around in the world ocean, we start to have the closing of the oceans on the southern and eastern margins of Laurentia that ultimately gives you the Ouachita origin in the Pennsylvania, and the arrival of the Yucatan block as part of that, and this whole sort of Ouachita mode along with these ancestral Rockies. We'll get to that in a sec. Then in the Triassic, mid-Jurassic, we have a phase 1 of continental extension that is taking continental crust and just stretching the heck out of it to give you what would be called a hyperextended crust that's partly mantleizes very thin and may in fact be exhumed mantle underneath what then becomes the thickest part of the salt basin in mid-Jurassic time. And then finally Jurassic, earliest Cretaceous time, when we're actually opening oceanic crust in the Gulf of Mexico, creating the rift in the Chihuahua Trough and down in Mexico in the Sabinas, and the rest of the margins subsiding thermally and beginning to receive thick sedimentary sections. So we'll just go through this very quickly. You'll be familiar with aspects of this, but I think it's useful both to see the graphics that we're using, but to kind of get a flavor of the story. These very nice global reconstructions are from Ian Norton and group at University of Texas Institute of Geophysics, their plates program. We had them kind of be Texas-centric so that we can see what's going on. In the late Neoproterozoic, Laurentia is attached to Amazon and Kalahari areas in the end of Rodinia, a supercontinent, but it's starting to split apart. Watch Texas as we go into the Cambrian. Now Laurentia and Texas with some offboard block. That little ribbon sausage in there is called Cuyania, and you'll watch it for a sec here. When we go to the Ordovician, well, North America has moved kind of southeast relative to South America. It's moving along strike. But Cuyania manages to transfer itself over onto the South America and can be found today in the Argentine Precordillera. So there's actually like Ellenberger equivalents out there, right? So it's a really interesting bit of North America. It has the fossils, it is a part of Laurentia that exists now in South America. So that's got to be part of this story, and it had to come off from something essentially off of Texas. Where it was, we don't know. The details are hard to go, but hard to determine, but that's where it came from. So how do you put that on a statewide map? Well, there's Cuyania I'm mentioning. How do we put that on a statewide map? This is an inferred map for the Ediacaran, which is the latest Proterozoic, post the global ice ball, snowball Earth, so after the glaciations, but before the commonly accepted Cambrian with shelly fossils. The really into middle Cambrian, about 525 million years, is the date of a lot of the igneous rocks up in, say, southern Oklahoma that are related to this event. So during this time we have igneous activity in the Wichita Mountains, in the Arbuckle, all the area in southwestern Oklahoma, probably extending east and south along the old edge of Proterozoic crust, or the present edge of Proterozoic crust, I'd say, something like that in there, where it's labeled igneous high. There's probably a second one of these things down the Devil's River uplift. It's only known from a few samples, and it's not very well determined, but it pretty well needs to be there. And there, likewise, gravity suggests an igneous high and extension, and the next diagram will also show that, off into the area south of San Antonio. We have actually the Van Horn sandstone in West Texas turns out to be Middle Cambrian, and it's filling essentially a half-graben situation out there. So it's part of another one of these, an extensional axis that probably extend quite a ways west of Texas as well. In the Gulf Coast, what's now the Gulf Coast area, we have blocks that are being pulled away, and we see this, of course, in contemporary rifted environments, North Atlantic, pulling off blocks like the Flemish Cap and Rockall Bank and these kinds of things. So we have blocks of thicker crust and thinner crust pulling away. Sabine block is a great mystery, actually. That's one of our #1 mystery in Texas. We know it's a microcontinental looking block from gravity, but we really don't know what its affinities are. It could be part of Africa, Gondwana, that showed up in the Ouachita. That was Bill Thomas's model. Just as easily could be part of Laurentia, though. We really don't know. It could be anything. It could be some third-party thing. We don't know. It'd be really great to find out. But also this Quiania block, which I've interpreted here basically as a ribbon continent like Japan or New Zealand, those kinds of things. It pulls away during extension and exists somewhere offshore. The only current stratigraphic evidence for these basins that formed during this time really begins in the Marathon and Ouachita basins, which themselves have to be transferred back to their original site of deposition. What we see today are thrust sheets that are bounded by a flat thrust fault that occurs in the Upper Cambrian. So we really, you have to take those things back, and there's some kind of basement they were deposited on, and we don't see it. So that's just an indication of where they're coming from. So if we go on to the later Cambrian and the lower Ordovician, the Ellenberger time and the time of the Wilburns and Riley in central Texas, we have this picture. So we have a platform in blue. We have a boundary that we don't really know how big or just where it was, and then you go into basinal environments in the Marathon and Ouachita basins. These basins were unstable. Particularly the Marathon Basin has evidence for a lot of probably seismic activity and things going on down there. The Ellenberger and Cambrian get thickest near San Antonio, actually. So they're not really defining the West Texas Basin. We think somewhere in about the end of the lower Ordovician, Quiania gets stripped off into South America, and what we develop then is an open margin that's very cherty. It deposits a lot of silica that we see in the basin as the Arkansas novaculite, the Caballos novaculite. We see it back on the shelf in the Montoya. We see it in spades in the Riston and the Devonian, in both Oklahoma and West Texas or Tobosa basins. Then in convergence, the late Paleozoic, we start here with the Devonian. Here, Laurentia is kind of floating out there in the world ocean with passive margins around it. But then it collides in the Pennsylvanian with a very hard collision with Africa on the eastern shores on the Appalachian Mountains of Laurentia. But in southern part of Laurentia, our part, Texas, we see this collage of stuff going on and not a very solid closure, really. And there's also, well, I won't get into all the details of it, but finally when we get to the late Triassic, this is kind of the closed configuration going forward into the Mesozoic. And just to put these up pretty rapidly, Mississippian, we start to fill in these deep basins in the Ouachita and Marathon with thick sandstone shale sequences, probably continental scale submarine fans. We of course have the source rocks on the Mississippian, Barnett shale equivalents. Then into the Pennsylvanian, we see the Yucatan block is arriving. Yucatan and Sabine are moving north-northwest, and the Ouachita and Marathon basins are now everted. They're thrust out. The fill of the basins is now thrust out and up onto the continental margin. Those are the blue arrows kind of showing there. So we take, in generating 4 deeps, like 33,000 feet of lower in the Atoka and the Ouachita, so I mean, big guys. And we start to see a little bit of sandstone coming off it in North Texas. So a real mixed environment, and at this point is when we start to see these brown uplifts of the ancestral Rocky Mountains. And there's a whole other story, which I actually won't go into here because it's take another 10 minutes we don't have, about whether and how you might refer the ancestral Rocky Mountains to the Ouachita Marathon. It's not clear to me you can, honestly, or should try to, really. But we can get into that separately. So finally, when we get to the late Pennsylvanian Wolfcamp, the Ouachita emplacement is essentially completed. There are thrust belt highlands in southeastern Oklahoma, probably down into Texas to a degree. However, behind that, if you go in the Sabine block, we still have marine carbonates, right? So that's one reason to say it's not a hard dock, you know, that there are remnant ocean basins, there are remnant shelf basins existing behind the Ouachita thrust. And we don't know their configuration because they've only been seen in occasional wells. But they could be pretty extensive. We think they would be. West Texas is subsiding at this point. So we have this lot of thrusting. We have surprisingly little sediment being shed from it. And as you go into the Pennsylvanian, or into the Permian, that gets even more pronounced. So there's more to be said there, but I won't do it right now. We go further into looking at this margin that's opened and closed. Now it opens again. So we're looking at the Gulf of Mexico, and the Triassic is the same one I showed earlier. Closed configuration. As we go towards the mid-Jurassic, a narrow ocean basin, an Atlantic basin, opens up between North America and Pangaea, Gondwana, South America, and Africa, who have not yet separated. that narrow ocean, if you look at those two together, look at North America, what's really happening is North America is floating off to the northwest. It's being rifted off of a unified continent, right? So that's kind of the best way to think of it. It's moving off to the northwest. We're generating a narrow, sort of constricted ocean basin, right? And this is actually essentially at the time of Luan salt deposition. So it is a dry basin of nearly oceanic depth that then is now starts to receive enough seawater to evaporate and form salt deposits. Then as we go into the mid-Cretaceous, that Atlantic Ocean is opened widely. Yucatan has kind of rotated out to form, and ceased rotating to form the Gulf of Mexico, and we're going more towards our present configuration. So just to look at that briefly, I talked about this some at the meeting last week, but a story that we can all live with, Department. We start with a closed configuration, and starting around 220 million years. There's about 60 million years of phase 1 continental extension. So we start with a series of late Triassic inferred grabenfels all the way from South Georgia to the Eagle Mills Formation in East Texas and the Arklatex area, to the Chitam anticline and other things down towards Mexico. There's some complexities in here, but basically it looks like we're looking at a beginning of a general northwest to southeast extension and with a series of transfer faults that are taking up variable amounts of extension from one sort of graben complex to the next. That's how it begins. If we look at some of those onshore, I went into this in more detail, but if you look at this is an isopack of Jura-Cretaceous in the East Texas, North Louisiana kind of thing that's happening is something that looks kind of like that. East Texas, a nice linear trough that is being pulled apart in this extension. You might have triangular sort of wedge basins, such as perhaps North Louisiana. And these higher blocks, which are higher blocks, mean you have thicker continental crust that's less extended than you had in the troughs. So there's a whole story involved with that, which I think I won't go into right here, but we can talk more about that. Same kind of thing in South Texas with the Pearsall Arch that I've been working on more recently. Here's a seismic line with some interpretation on it. There seems to be a significant Jurassic basin sitting northwest of the arch. The arch is a basement Paleozoic ridge sitting out there with later Jurassic and Cretaceous lying over it. And the way that kind of thing would form would be essentially a large sort of diffuse pull-apart structure here within in the area northwest of Pearsall. There are lots of big linears in Mexico, and they define their thick and thin continental blocks. They're all very nicely defined because they get reactivated in the laramide, and so you see them in the surface geology actually in that area. By the end of phase 1 then, we've been extending the continental crust northwest-southeast direction through this whole area to the point where many parts, particularly the darker green areas, probably have much less than half the original thickness of crust. So we're down from 40 kilometers, we're down to less than 20, in many areas probably less than 5 or 10. The hyperextended areas can even be less thick than oceanic crust and may have mantle, maybe exhumed mantle. So we don't know because they're in the deep parts of the Gulf of Mexico primarily when they're not drilled. But in those deep areas, which were lying, if you do that and look at isostasy, those areas would have been lying, a mile, 2 miles below sea level, okay? But they're dry, right? Subaerial basin. And because the water, the marine world ocean hasn't gotten into there yet. So they're sitting there in a very hot, very dry environment, similar to the Afar Depression, only probably bigger and deeper than that, more like Death Valley, but on a very large scale. And then into that, we start feeding marine water. And it falls down into here. There's various ways people try to do that. But it comes down into here and desiccates in the basin and starts to fill it up with several kilometers worth of salt. Okay, so it starts to fill it up. Some people think it fills it all the way up to sea level. And I'm not saying it isn't. But it goes back into these interior basins, East Texas, Mississippi, and so on, really outlining these areas of high degrees of extension that have existed before then. So this is at 162 million years, probably goes into the lower Oxfordian, and then we start to open oceanic crust. So this is the vertical gravity gradient map that's been presented recently, and everybody has a picture based on it. It's a beautiful outline, and actually in the vertical, I didn't put the uninterpreted version, but you can actually see transform faults and spreading centers out in the Gulf of Mexico, and be somewhat reliable about what you're doing with them. So this is my guess at what's going on in there. we have spreading and formation of oceanic crust in the deep Gulf of Mexico. We have a continent-ocean boundary established that jigs and jags out along the basically the slope, upper slope environment today on our side. And it's a rotational opening where Yucatan is being rotated some 40 degrees or so, and I've given a 42-degree rotation and shading here just to see what that would look like. And there's a few side issues involved with it, but that's essentially the rotation that has to really be had for that. What's going on in that environment, once oceanic crust is forming, after the salt, after collovian, that's some Oxfordian Cambrian time. It's also the same time that we see extension in the Chihuahua Basin beginning, we see extension in the Sabinas Basin, and up into the Bisbee area, southern Arizona. It's an area that's called the Borderlands Rift System that's interpreted as a Backarc rift. So you've got Mexican arc processes, we've got subduction and volcanism in Mexico, and that generates an upwelling of mantle that generates extension behind the arc. Common mechanism, we see it going on today in the Western Pacific. The idea is that this was happening here and opening up this whole series of yellow basins behind the green arc. I don't know why the arc is green, I have no idea, but it is here. And that this same idea that Bob Stern had was that this same thing was going on in the Gulf of Mexico, and you've got to interpret them all together. I don't quite do it the way he does it, but what we do see is we have a lot of magma in the Western Gulf, not so much in the Eastern Gulf, and it ends up rotating Yucatan. That's my game. Anyway, however you do that at the end of phase 2, it looks like this. This is lowermost Cretaceous, earliest Cretaceous, right? And finally that ocean crust stops rotating, it stops being created in the Gulf of Mexico, and everything's dead in the Gulf of Mexico after that, from this point of view. Now, as soon as oceanic crust begins to be generated, so in the Oxfordian, the continental margins that are on continental crust have essentially no further tectonic activity. None that's been documented. So they start to subside. They were held up by hot mantle. Everything was going on. Now they're starting to subside, and as they subside, they start to receive sediment. We start to build the basin margins, beginning with the Smackover carbonate margins, and then into a whole series of clastic infills. And we have that whole story of the Mesozoic Cenozoic that goes on in the Gulf of Mexico, in our Gulf Coast Basin, the northern western Gulf of Mexico. So that's the short story for that. I want to leave you with one last set of slides. I can just about whiz through these. Looking at one of the really interesting story to my mind from Oxfordian on is to look at the position where we might have Texas rivers. Because on the series of statewide maps we put together, the depositional systems in the Gulf are pretty well known. They've been Bill Galloway and all these people. We have really good ideas of how that kind of thing worked. It's nice to put them on a statewide map. But we also have some knowledge from West Texas and various places. So we know something about where highlands were, because we know something about where rifting was, we know where uplift was. We know where the basins and the depositional systems were. How do we connect those dots in a consistent manner? So we'll just kind of flick through these series of statewide maps, and you can absorb that. In the Oxfordian, we probably have a continuous system of highlands that are rimming all this extension we were talking about in the Gulf of Mexico. So, and we don't see a lot of clastic input. It's pretty much carbonates, except right up against the margin. But when you go to Tithonian, now you start to put the Cotton Valley into this picture. We have a big delta system in East Texas, right? Not so much in South Texas going on, but in East Texas we have big delta, which has been called the Lone Oak Delta. Once big deltas are fed by big rivers. Big river is Lone Oak River. What that means is that the highlands have been breached in that area, right? This is no longer a continuous highland. And in fact, the Lone Oak is reaching significant sediment sources, and right at this time is when the Chihuahua Trough in far west Texas is being extended, and the flank of that is an arch, is a basement high that gets uplifted generally. It goes all the way into Arizona, actually. Here I would call it the Waco Arch, probably, but that's a really good sediment source for a river system feeding the Cotton Valley and Houston units in Texas. As we continue in time into the early Cretaceous, the Aptian, the river systems die down. Probably the highlands are getting lower, or we're losing some continuity. When we go into the Albion, of course, we're starting to flood back onto the continent from high sea levels, and we're generating the Glen Rose and basal antler sand. But we do have some rivers that we can define, the Paluxy, Cox, and so on, that at least drain significant local areas. Once we get to really the Albion and on, we're starting to really flood the entirety of the state. So at the Eagle Ford time on the left, the entire state is underwater. We do have the Woodbine Delta being fed very significantly from the Oklahoma area, perhaps some from from the southern Arkansas area, the Arkansas area, where we have significant uplift. We do have an uplift, some of which extends into easternmost Texas. We are starting to see sources from the west in New Mexico, the Tres Hermanos Delta of this age, but it doesn't really make it into Texas. We're being blocked by the Ojinaga Trough around in far west Texas. We don't see those clastics coming in the Eagle Ford. But later on in the Cretaceous and the Campanian, we do start to see this enhanced clastic from the Cordillera, from the west. Coming through the Big Bend country, the Javelina and Aguja underlying the Javelina, in Campanian time on into and it carries on to the Maastrichtian. And we see clastics being put into South Texas, and I've defined two general river systems, an Olmus River and a Bigfoot River. We have really good evidence. We have deltas in South Texas around near San Antonio that are sourced from the north, which is the Llano uplift country, right? So either the Llano was uplifting as an independent sediment source, or more likely it was sitting as sort of a pedestal, creating an extended land area that we're getting additional sediment from the west. That's something a little petrographic and possibly detrital zircon work would be really interesting to determine those possibilities. But we definitely have major clastic pulse in there, whereas North Texas, largely marine claystones. Then into the Paleogene, now we start to see our present river system developing as Texas is mostly exposed and subaerial. And I've kind of used least astonishment, looking at present river systems that were particularly in size during the late Cenozoic. Before that, they were probably more freely wandering, but they do tell you something about where these systems should be. We also know where our major delta systems are in the Gulf of Mexico, and our major uplift and volcanic sources are to the west. So we'll just see these. There's a really odd alternation and oscillation in delta, amount of sediment that's being supplied to deltas. And one of the tricks is to figure out why that happens to be. In the late Paleocene, which is the lower Wilcox, South Texas doesn't get much of a delta, partly because most of that area is probably still underwater. That area had a lot of subsidence. Even though you've got mountain development going on, the sediment sources are not coming out into the areas where they could now be preserved. Major sediment sources in East Texas, a Rockdale River that feeds the Rockdale Delta, or much of it, that probably heads in the southern Rocky Mountains in Colorado and northern New Mexico. As you go to Middle Eocene, that system dies down. Queen City Delta is quite smaller, but there's a big delta system in South Texas, as there was in the upper Wilcox or the Carrizo. And that indicates we've got subaerial exposure, major mountain development in Mexico, which is much of it is of Middle Eocene age. We do have uplift, probably the Sabine Arch during this episode also, and that, when we get to the middle late Eocene here, may be feeding a little bit of an enhanced sediment source for the Rockdale River to form the Yewa deltas in southeast Texas. We start to see volcanism in West Texas. That becomes a significant sediment source, particularly going into the Oligocene, as shown on the right-hand slide. So there's a lot of detail in there which we won't have to go into. When we get to the Miocene, we start to see the uplifting and unroofing of the Balcones area of the hill country, really all the way into North Texas, down to the Pecos River country. Really, you can think of where that is by the areas where we have incised river systems, incised meandering river systems, right? The Brazos, the Colorado, and so on. Define this area of uplift. There's also some uplift in East Texas. And you've got major river systems. Our major river system in the late Miocene tends to be through the central part of Texas, which could be a Brazos, Colorado kind of event. We have the Oglala deposition in West Texas, a lot of which is known about, and these river systems went all the way back up to the southern Rockies. But later on in the Pliocene, they get beheaded by the Pecos River and the Canadian, take over the drainage from the southern Rockies, leaving the southern high plains perched and eroding as they do to the picture on the right at present. The Rio Grande drainage system only integrates during this period of time, so that's yet a different story. So there's a whole a story about these river systems. A lot of it is not known because we don't have preserved rocks in that intermediate area, but I think we can tell a lot about what's going on. With that, I think I'll leave you. I'm certainly happy to answer questions or elaborate on various ideas and just share with you the excitement of Texas geology. Thank you very much.